everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about very few important terms which we encounter in data structures. So let us see what binary search tree is, what is an AVL tree, what is MV search tree, and what is the concept of hashing. Have to overcome the collisions which encounter in hashing. We are going to just go through the basic terms that we encounter in all these concepts. Let's start with binary search tree. So before going to binary search tree, let's get an overview of what a tree is. A tree is a non-linear data structure where the cardinality between the data elements is not one-to-one. It can be one-to-one, but it is not mandated that it should be one-to-one, just like your linear data structures. Coming to the general classification of trees. So here I show you a small taxonomy of trees. A tree can have any number of children. When you put a constraint on it saying that it can max have 2 children, then it converts into binary tree. Binary, the word itself tells that 2. So when we put a constraint that a node can have maximum 2 children, then it is a binary tree. We can further put constraints on the same and we can convert that into a heap or a binary search tree. Then what do you mean by a heap? Heaps are further classified into 2 categories. One is min heap, the other is max heap. Then what do you mean by minimum heap? A minimum heap is a heap tree where the parent value is minimum when compared to its children. Right? Max heap is a heap where the parent value is max when compared to its children. Heaps do not tell us any relation between the content present in the children. It puts only constraint with the parent. It gives a guidelines only to the parent saying that if it is a minimum here, as you are a parent, you must have a lesser value when compared to the children. If it is a max heap, as you are a parent, you must maintain a higher value when compared to its children, right? So it does not put any constraint on siblings, right? So this is heap. The second one, a contrary to that one, is binary search tree. A binary search tree brings a constraint on the 3, the parent, left child, and right child. Its constraint binds all 3. In what manner is the parent value must be greater than its left child and must be less than the right child. Let me show you this in the picture. Have a look at this one. If the parent node value is k, then the left child's value must be less than or equal to k and the right child value is greater than k. So such a tree is binary search tree. Have a look, all the left, parent and right. There is a bonding between all the 3. Right? So such a tree is binary search tree. So have a look at a small example of the same. Right? So randomly let me start from the root. So the children who are present in its left subtree all are having a value less than the root. Whereas all the children who are present in the right subtree are greater than the root. Right? This theory works for all the nodes. Right? So let me take a random example of this subtree which is headed by 40. Right? Its left value is 34 which is less than 40 and its right subtree values all are greater than 40. Okay, this property is recursive in nature. Okay, such a tree is binary search tree. So what are the basic applications? So if you go for in order traversal of binary search tree, you will get the data in ascending order. It is very helpful in representing arithmetic expressions and storing the data if the data is sorted in nature. And it is used in Unix kernel for managing virtual memory to access to create virtual memory. BSTs will be used in Unix kernel. These are the major applications of BSTs. So the basic operations that we are going to perform on binary search trees are search, insertion, and deletion. The first operation is, let us look at insertion. How to insert data. Simply create a node. If that node's value, if the root is not existing, it is empty, then make this node as the root node. If the tree is already existing, compare its value with the root. If the value which is in my hands is lesser when compared to the parent, that is the root, send it to the left subtree. Recursively do the same. If the value which is in my hands is greater than the parent, send it to the right subtree of the root. Even this is going to be recursive. One thing you have to understand is, with every insertion operation, the new node which comes into the picture will settle as a leaf node. Okay, right. So let's construct it with this random list. Okay, the first element is 25. As a BST is not existing, now 25 will be the new root. Okay, now coming to 15, how to insert 15? As 15 is less than 25, it will go as its left child. Coming to next value 50, compare it with the root. Always start with the root, guys. Always start. Whether you want to search, insert or delete, start with the root node. Right. Next element is 50. As it is greater than the root, insert as the right child. Next 10. Start with your root. Go to your left as it is less. Here you encounter another value 15. 10 is less than 15. So it will go and settle as the left child of 15. Okay. Right. Then 22. Again start comparing from the root. As 22 is less than 25, go to the left side. Compare it with 15. As 22 is greater than 15, make it as the right child of 15. Right? Next, 35. As it is greater than the root and less than 50, it will be the left child of 50. Next is 70. It is greater than 25, so right side of 25. Greater than 50, right side of 50. So 70 will be the rightmost element. Next level, 4. So as it is less than 25 the root, go to the left side. Compare it with 15. Less than 15, so go to the left. Compare it with the 10. Less than 10, insert it as the left child. Okay, now go with the 12. Even 12 is less than 25, 15, but greater than 10, so right of 10. Okay, so the next element that I'm going to encounter is 18. It is less than 25, but greater than 15. So go to the right side, compare it with 22. It is less than 22, left child of 22. Next is 24. Less than 25, so left side. Greater than 15, so right side. Greater than 22, so right side. Right? So the next element is 31. When you talk about 31, it is greater than 25. So go to the right side. Compare with 50, less than 50. So go to the left side. Compare it with 35, less than 35. So left child. Next 44, greater than 25, less than 50, greater than 35. So right child of 35. So next is 66, greater than 25, 50, but less than 70. So left child of 70. Next 90, greater than 25, 50, 70. So the rightmost element will be 90. This is how we were going to construct a binary search tree. You might have observed that With every key value insertion, it is going to get settled as a child or a leaf node, external node, you can say. Okay, so have to delete. So while deleting, we have three different cases, my dear. Please keep these three different cases in mind. One is a case where you are trying to remove a leaf node. When you remove a leaf node, nothing is going to go wrong. No problem at all. Delete it. Okay. So here I try to delete 7 as 7 is the leaf node. Delete it. It is not going to disturb or it is not going to disconnect nodes in your binary search tree. A second case is a case where you are trying to remove a node which is having a single child, one child. Say for example, 10 over here. If I try to remove 10, then if I directly try to remove 10, the tree will be broken into two halves, right? The link between 8 and 14 gets broken. So build a relation between the child of 10 and the parent of 10. That is a relation between the child and grandparent. Okay, then remove the element. Have a look at this one. So when I remove 10, 8 get attached or related to 14. Right? So say in a blunt way I can say if parents expand, grandparents will be taking care of their grandchildren. Same point over here. If 10 is deleted, 8 is going to take care of 14. The remaining structure of 14 and its children will be as it is. It will not be disturbed. And you can see that with every deletion, the BST property is not altered. Is not altered at all. The third case of a deletion is, okay, let me look at one more example. I try to remove another node with single child. Even that didn't disturb, right? So now the third case. What if you are trying to remove a node with two children? A binary search tree can have a maximum of two children, right? What to do? So the node which you want to remove can be replaced by its successor or predecessor. Choose one of the sides. Okay. Successor is the leftmost element of the right subtree, whereas predecessor is the rightmost element of left subtree. I'll show you an example. Wait. So here it is. I want to remove 3. So in the rightmost element, rightmost tree, the leftmost element is 4. Either replace it with 4 or in the leftmost 1 is the element, you can replace it with that. Here I have chosen the successor 4. So I have replaced it with 4, right? But the BST property did not change. So what if I remove the root itself? Even you can do that, right? If I try to remove root, here I am going to work with predecessor. That is, in the left subtree, what is the rightmost element? 7. Replace the root with 7. That is the predecessor. This is how it is going to look like. This is deletion in binary search trees. 3 different cases. A case where you are trying to remove a leaf node, or a node with one child, or a node with 2 children, right? So these are the 3 different cases. And then BST is good, binary search tree is good, but it suffers with a property. What if the elements which are being inserted are continuously smaller than the root? Or I can say that if the list of the elements which are given to you to construct a BST are ascending in order or descending in order, then you will get either left skewed or right skewed list. Right skewed binary search tree. That is, it is going to increase the height of the tree either in left or right direction continuously, whereas it is not balanced. That is, one side it is keep on growing and the other side no one is taking care of that. So to balance the things, balanced search trees have come into the picture. Balanced search trees are an extension of binary search trees. They are no different, but they balance. How they balance is, after every insertion or deletion, the balance factor of all the nodes is considered from the root to the leaves. Then what is this balance factor? It is nothing but the difference of height of the left subtree and height of the right subtree. It should be either -1, 0 or +1. Any one of these three values. If it goes beyond that, we can say that that particular node is the one which is the root cause to imbalance the tree. We will balance it. Then how we are going to balance it? Using rotations. Okay, we can, based upon the situation, right? Based upon because of which element this imbalance has occurred, we are going to choose one of these rotations. So these rotations are broadly classified into two categories: single rotation, double rotation. Single rotation is a one step of either left rotation or right rotation, whereas double rotation is a two-step one. Either you can go for left right rotation or right left rotation. Two are there. Okay, so these are the four rotations which we have, using which we can balance the tree. Okay, so please keep in mind, AVL trees, that is balanced search trees, are BST in the core. So let me explain you what these rotations look like. First is single left rotation, LL rotation we call it in a short form. So have a look at this one. When while inserting the data, first I inserted 1, no problem, balance factor was 0 because it is single node. When I inserted 2, as 2 is greater than 1, it will become the right child. Right now the balance factor says 2 is a leaf node, so its balance factor is 0. Coming to 1, 0 minus 1, it is -1, no problem. Coming to the insertion of 3, as it is greater than 1, 2 and 3, it is be the rightmost element. Let's again calculate the balance factors. So the balance factor of 3 is 0, 2 is 0 minus 1, which is -1. Coming to 1, it is 0 minus 2, which is -2. You can clearly see that 1 is the node which lost its balance. Now, think in view of 1. Why it lost its balance? Because of inserting in the right subtree, a new right node has come into the picture. Because of 3, 1 lost its balance. So, left rotate. So, pull 1 towards left. Once you pull 1 towards left, 2 is going to go to the top. 1 will get the position of new left of 2, and 3 will be as usual the right of 2. Right? So have a look at the BST property. The root is 2. The value on left is lesser. On right is greater. Now calculate the balance factors. All are zeros. Now we have balanced the tree. So this is how we are going to balance them. So next example. Right. For example, I am inserting in this order. First 3. Balance factor is 0, no problem. Next 2. So on its left, 2 is going to settle. So as 2 is a leaf, its balance factor is 0. Coming to 3, it is 1 minus 0, which is 1. Not a problem. Now I am going to insert 1. It is going to settle as the leftmost element. So the balance factor of 1 is 0. 2 is 1. 3 is 2. Now you can clearly see that 3 lost its balance. And please think in view of the node 3. Why it lost its balance? Because of 1. Then where 1 got inserted? In the left subtree, as a left element it got inserted. So now pull the head of 3 towards right to balance it. right? When you pull it, you are going to get this picture. 3 will become the new right child of 2. Now calculate the balance factors. Now the tree is balanced. Okay. These are the 2 scenarios of left and right rotations. Let's go for the combination, that is double rotations. So left, right rotation. Have a look. What if the order is 3, 1, 2? I inserted 3, balance factor is 0, not a problem. Then I inserted 1. So it will come as the left child of 3. Balance of 1 is 0, 3 is 1. Now I insert 2. 3, 1. As 2 is greater than 1, it will become the right child. Now again calculate the balance factors. Have a look. The balance factor of 3 is 2. 3 lost its balance. Why it lost its balance? Because of 2. Because it is the new entry into the tree, right? Very good. Then where it got inserted? In the left subtree as a right child. So LR rotation. Have to do this LR rotation. Very simple. First left and then right. Left of what? Left of the affected nodes. Left subtree will be rotated left first. Then the affected node will be rotated right. That is 3 will be rotated right. In this scenario, first the left subtree of 3 is headed by 1. So it will be rotated towards left first. When you get a resultant one, now pull the affected node, that is 3, to the right side. So now the tree is balanced. A contrary to that is right-left rotation. Okay. After inserting 1, 3 and 2, you can clearly see that 1 lost its balance because of insertion of 2. Where 2 got inserted? In the right subtree as a new left child. Right subtree as a left child. That is right-left rotation. So first I am going to perform right rotation, then left rotation. Very good. Right rotation of what? Right rotation of head of right subtree of the affected node, which is 3. Rotate it. Now rotate the affected node towards left. Right? So now this is the balanced tree. These are the 4 rotations based upon the newly inserted element or the element which you have deleted. You are going to identify the nearest node which got affected and perform an appropriate rotation. Okay, then you can clearly balance the tree. Now let's have a look at an example. This is a random list I have taken and I'm going to perform. The insertion will be same as it is as BST. There is no change in it. Every node which you are going to insert will settle as a leaf node. There is no change in it. But at every step, a new step is added, which is calculating the balance factor of all the nodes. If the balance factor disturbs, we are going to rotate them. Okay, very simple. 63 is the first one. As it is the first one, its balance factor is 0. Next, insert 9 as a left child. Now calculate the balance factors. No disturbance. Next, 19. Now there is a disturbance. You can see that 63 got affected because of inserting 19. Where 19 got inserted? In the left subtree as the right child. So LR rotation you are going to adopt. So in LR rotation, first of all, rotate 9 towards left. Right? Then 19 will be headed. Now rotate the affected node 63 towards right. This is the result. Right? So now do this as now again calculate the balance factors, my dears. So once you calculate, you can see that it is a balanced one. Now insert the 4th element, which is 18. Right? So this is done. Next element 18. Done. No problem at all. 108. No problem at all. 99. Again calculate the balance factors. No problem at all. 81. You can see that because of inserting 81, all the nodes, 3 nodes got affected. Totally 3 nodes got affected. Now our point of concentration must be the node which is in relation nearer to the inserted one. If you look at it carefully, parent of 81 didn't get affected, but grandparent got affected. Now 63 in relation to 81 is grandparent. So forget about grandparent. So think of only grandparent. If you can balance your grandparent will get convinced, not a problem. So in view of 108, 81 got inserted as the left child in the left subtree. So right rotation. So rotate it right. Now have a look at this one. Once the grandparent got satisfied, all his ancestors got satisfied. Now this is a balanced search tree, popularly known as AVL tree. Okay, so these were the rotations which we have adopted while inserting the data. What if we are trying to delete the data? Deletion the data, the same old 3 cases of binary search tree, which is deleting a node, which is a leaf node, a single child node, or 2 children node will be the same. But once you delete it, calculate the balance factor. If it is imbalanced, kindly adopt one of the balancing technique and stabilize it. That's what. So in this tree, what if I remove 81? If I remove 81, you can see there is no problem. If I remove 27 in this current tree, 63 is going to get affected. Why it got affected? Because of removal of 27. So what kind of rotation? Left rotation. You can clearly see this, guys. It is -2. Negative value itself tells that the right hand side weight is heavy. If the right hand side weight is heavy, shift some load towards left. That's it. Left rotation. Now it is balanced. Okay. So these are few. Now in this tree, try to remove 18. The root gets disturbed. If the root gets disturbed, kindly rotate 19 towards left. Right? It is -2. On the head of 19, you can see the balance factor is -2. That is, it is right heavy. If it is right heavy, go for left rotation. Pull it, bring it down and make it balanced. So coming to the applications of AVL tree. Insertions and deletions are not that frequent. Wherever or the application, that is whatever the database you are trying to go for, if it does not have insertion and deletion on a frequent basis, AVL trees are best. Only if search operations are the main, that is the database is stable, rarely we insert an element or rarely we delete an element, but searching we frequently do, then AVL trees are the best. Okay, so short search time is needed and input data is sorted or nearly sorted. In that case also, AVL trees are best in case. Okay, the basic drawback with AVL trees, limitations, let me tell you. So after every insertion, the insertion technique is very simple. Frankly speaking, very simple. It is just like your BST, but calculating the balance factor after every insertion and deletion is very time consuming. Okay, which is of order log n, which is a bit high. So as we went for non-linear data structures, the complexity is supposed to decrease because the elements, more than one element is related to more than the other elements, right? So as we have data, more each node holds more and more data of its neighbors, it must be very easy to navigate. But these calculating the balance factors is a tedious task, time consuming task. So to overcome this, we cannot change the fund of AVL. The AVL tree is as it is. So to overcome that, red black trees have come into the picture and many more. Okay. So this property of AVL, that is rotation after every manipulation, cannot be changed. That is the root point of AVL. Okay. So these are the few applications of AVL trees and few limitations. Right. Coming to an extension of the same. MVSH trees. Guys, remember, recollect your points. A tree can have any number of children. So each node will hold a data point, right? When you put a constraint that only 2 children it can have, binary trees have come into the picture. Each node will have a data point. Again, I have kept a constraint saying that left child value must be less than parent and right child must be greater than the parent. BSTs have come into the picture. Very good. Even here, a single data at every node. Next is AVL trees have come into the picture, where I have calculated a balance factor also, and still you can see that every node have in all, whether it is a tree, whether it is a binary tree, whether it is a BST, AVL, whatever trees you have seen till date, you can see that every node have a single data value. Then people thought of why we are forced to store a single data value at every node. Can't we extend it? They have extended it and they have come up with multi-basic trees, or simply you can say MV trees of order M, where a node with n children can have n minus key values, right? And they have also given the fundas. The nodes are in, the keys in the nodes are in ascending order. That is, the children on left of ith key are less than I value and right of I are greater than ith value, right? Let me show you pictorially. Have a look at this one. Order of 8. Order tells you about the number of children it can have. If it can have 8 children, then it can have 7 intermediate key values it can hold, a particular node can hold. Then coming to the nature of these keys. So all the children which are left to K1, that is C1 children, are having a value less than K1, and the child C2, which is on the right side of K1, will have a value greater than K1, right? That is very simple. For every key, left hand side children will have less value, whereas right hand side children will have greater value. And between K1 to K7, the nature is these keys are in ascending order. K1 is less than K2, K2 is less than K3, and so on. See how beautifully they are designed. You can clearly see that BST property is prevailing. Did you lose that search property? No. But we extended BST by providing more than one data value at every node. Okay. So let's go with the properties of B trees. B tree is a self-balanced search tree, okay, with multiple keys and has more than 2 children. Okay. So the first property is all leaf nodes must be at the same level. Second property is except the root node, all the remaining nodes must have at least m by 2 minus 1 keys or maximum m minus 1 keys. As it is of order m, definitely it will have m minus 1. Okay. Third property is it about non-leaf nodes. Except the root must have at least half the children must be filled. Okay. So, and the key values must be in ascending order and all. Okay, so B tree is also known as height balanced MV search tree. It is very important, guys. This point is very important in your competitive exam point of view. B tree is also known as height balanced MV search tree. Okay, then where these B trees are used. So as it reduces the number of reads made on the disk wherever you need. So it is going to optimize the size, and it is help you in handling bulky amount of data and implementing databases and file systems and reading and writing huge blocks of data. It will help you. Have a look at a small example of B tree of order 4. As I have said, order 4, 4 children you will have and 3 keys you will have. So have a look at this one. All the children left of 30 are less than 30, whereas right of 30 are, this is the tree subtree, which is right of 30 is greater than 30. In view of 70, left of 70, the same tree is having values less than 70, and right are having values greater than 70. Okay, so and we can say that right of 30 will be equal to left of 70. You take whatever wording is easy for you. Both are talking about the same subtree. Okay, basic operations that we can perform. The same old search, insert, and delete. And it will be similar when you have learned BST. These are quite simple, and their complexities is order of we go of log n. Okay, so search operation, very simple. Read the input which you want, compare the search element with the root node keys, and identify. If the key is not present in the root, then identify the nature between what values it can be and go in that direction until unless you reach the leaf node. The same process with the insertion. Read a value and check which is the appropriate position if the tree is not empty. If it is empty, this is the first value and it will act as the root of the tree. Okay, if the node which you have read is value which you have read in is and the tree is non-empty in nature, compare with the elements keys present in the root and identify in which direction you have to move. Either the leftmost, mid, rightmost, in between the values, guys, between. Okay, you do and search, and if you find a node where the current node is supposed to be present but it is full, then split it, break it into 2 halves and insert. Let me show you it example. So I am considering a B tree or MA search tree of order 4, that is 4 children I can have and 3 key values. And please remember that the nature of keys within a node is ascending order in nature. So I inserted 5. Next, I'm supposed to insert 3. If I want to insert 3, I have to sort and insert. So 3 and 5. Next, 21. Last place is vacant. Give it a place. When you come to 9, 9 is supposed to sit between, when you sort it, it is supposed to sit between 5 and 21. But this node cannot accommodate it. So the mid value is 9 itself. So send it to the top. So make it as the root. If I make 9 as the root, its left children will be 3, 5 and right children is 21. Okay. The next element insert. The next element is 1. If I try to insert 1, I cannot place it over here because this node will become unsorted. But my keys must be sorted in nature. So I'm going to move 3 and 5 right side one step and I'll make a vacant place for 1 and I'll insert it. Next is inserting 13. The same story. I cannot, 13 is greater than 9. Definitely it will go to the right side of 9. So I cannot place it over here because 21 and 13, they don't sit. It is descending order. Okay. So I'm going to swap or I'm going to sort them. Sorting will be the appropriate word. I'm going to sort them. Next, what if I try to insert 2? If I try to insert 2, its right position will be 1, 2, 3 and 5. But the node cannot accommodate 4th element. So the mid value is 3 and it will push it to the top. So now the root can accommodate, because 9 is having 2 empty spaces. It is going to give space for 3, right? So it has given space for 3, and this is how it got split. So as 3 went to the top, 1, 2 are the left of 3 and 5 is right of 3. So you can clearly see that 5, you can call this node as right of 3 or left of 9. Both are one and the same. Now I inserted 7. It is having an empty space. Well and good. Next. If I try to insert 12, the appropriate place for this one is here, between 10 and 13, as the keys must be sorted in nature. But this is not possible. So that is, the node cannot accommodate it. So push it to the top. So 13, the mid element, 13 is going to go to the top. And this is how it is going to split the elements. So one more insertion, 4, 5, 7. This is the new insertion, my dears. Next insertion. So if I try to insert 8, so 7 is the mid element. It will go to the top. Even the top cannot bear it, my dears. So the correct order will be 3, 7, 9, 13. The mid element is 9. 9 will form the new root. So now the left of 9 is 3, 7. Right is 13. Left of 3 is 1, 2. Right of 3 is 4, 5. Right of 7 is 8. Left of 13 is 10, 12. Right is 21. This is your final list. After insertion, this is a proper ordered 4-MV search tree, right? Then have to delete. Delete if the node is a leaf node, no problem. Delete it. Then, guys, we need at any point of time, all the properties of MV search trees must prevail. The properties which I have said, half of the key values must exist. So if deleting a node is not going to balance it, then fine, go with it. If not, whatever will be the case. Then if the leaf node does not contain m by 2 keys, then complete the keys by taking the elements from left or right sublinks. But if taking the element from the left or right sublinks make them imbalanced, then push them to the top and split them, right? And if neither of them can help you, then merge them. Merge the parent. Okay, I'll show you with an example. You need not worry about that. Have a look at this one. In this tree, if I try to remove 65, what will happen? So very simple. If I remove 65, 90 is the only one. So all the elements which are left to 90 will get merged, right? Or you can bring 70 to the top to fill the vacant. Right? Now delete 70, merge them. Delete 100, send it up. If very simple, guys, if I remove 100, the right of 90 will be lost. So send 80 to the top and bring 90 to the right side. Now what if I remove 80? That is one primary question. If I remove 80, send 60 to the top. Okay, this is your final deletion in case of MV search trees. Okay, so we have seen what is a binary search tree, AVL tree, and MV search tree. Let's look at few terminologies in hashing. Hashing is a technique for performing any task at a constant time. That is, storing the data in its short form. Short form with the help of hash function. If, for example, say a random phone number 9440382482. I have picked a random number, guys, and the other's number is 9440111222. Okay, so my database is very less. To store these values, what will be, is it efficient to take first 4 one? So if I take the first 4, then duplicates will come. Even A and B both will map to the same number. So it will be wise. It will be wise enough to take last four digits 24821222. They are unique in nature, right? So you have to identify the uniqueness. That itself is hash function. Okay, so if you perfectly implement and fill the hash table with the hash function, the order of insertion, deletion, or retrieval will be order of 1. But the word perfect is not present in this world as far as my knowledge goes. Everything has a flaw which we need to overcome, right? So what is a hash function? So it is a function used to map data to arbitrary size to fixed size. Then what should be the parameters to find a hash function? It must be easy to compute, evenly distributed, and minimum collisions. As I said, if I take first four values of the phone number, collisions will be there. If I take last four, I'll reach to some extent of uniqueness, right? So these hash functions are broadly divided into two categories. One is static hashing and dynamic hashing. Static hashing, where the sets of key are fixed and given in advance. You cannot neither delete those keys or neither you can extend the list. Dynamic, based upon your requirement, you are going to add that key to your hash table. Types of hashing. Various types of hashings are there, guys. So directly, without using any algorithm, no manipulation, directly send it to the table. But it increases collision. Redundancy will be there. So better go for modulo division. So that is whatever the key is there, mod division with n. Generally, this n value will be prime in nature, like 7 or 11. Okay, so whatever the result you get, store it. Hash function is supposed to reduce the size of the key. We want to reduce the size of the key such that it can be stored easily in the hash table with its unique feature, right? So for that. And the next method is mid square. Very simple. Take a key, for example, 3121, square it. You will get this result 9740641. Take the mid value, that is 406. Use it as the key. Even that is one of the solution. Next is subtraction. C is a constant, my dears. Constant. Subtract a constant from your keys and get the unique value, which is least way used one. Next is folding. Folding is an interesting one. So if the address size is 3, fold the data in 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Add them. Get the 3. If you get a carry, forget about the carry. Use the 3 bits or 3 digits as your address. That is one way. So that is shift hashing directly. Yeah, even you can have boundary hashing also, folded boundary. Alternate places are flipped on the boundary. That is 1, 2, 3, 7, 8 will be as it is. 6, 5, 4. The mid 3 will be reversed. I'm folding, right? So flipped boundary also you can have. That is one of the techniques. And pseudo random. Random function you can do, and you can have you can get an entry into your hash table with your key. For example, here I've taken a simple example, y is equal to x plus c, where x is your key and a and c are constants. You can use quadratic equations also. Okay, these are the different types of hashings you can do to get a unique value. Okay, so whatever the function you adopt, you will get collisions. That is the basic fun. So to avoid that, to overcome these collisions, have a look at this picture. Key 1 is mapping to block 4, sorry. Key 2 is mapping to block 1. Key 3 is key 2 is mapping to block 3. Key 3 is mapping to block 1, key 4 to block 2, whereas key 5 is again to block 1. That is key 3 and 5 got collision, right? So how to overcome these collisions? We have two kinds of collision resolution techniques. One is separate chaining, open addressing. Okay, in separate chaining, we are going to build chains of the data, right? So collisions will never occur. Okay, so have a look at this one. So very simple advantage is very simple to implement, as I'm going to take the help of linked list. At any point of time, dynamically I can create a node and I can bring relations with the remaining or existing ones. But the disadvantage with it is, if a node or an entry in hash table is not used, it goes on starvation, whereas the linked one goes on increasing, which raises the complexity of such. That is the basic drawback of your separate chain. Have a look at this example. For example, I want to insert 50, 700, 76, 85, 92, 73, 101, and my hash function is key mod 7. As I said, generally we use the n value as a prime number. I have taken 7. Okay. 50 mod 7, it will give me 1. So it is entered in the hash table at index value 1. Next 700, it's mod 7 will be 0. Coming to 855, its modular division value will be 1. So I have created a node and inserted. Right? So this is how I'm going to insert. If I get the values which are having more and more, when you go for modular of 7, which give rise to value 1 more and more, then chain with the 1, index value 1 will raise and the remaining go into starvation. That is the drawback, which increases the time complexity of insertion and deletion as well. Okay, so come to open addressing. In open addressing, we do not have any linked list. We do not use any extra space. Within the hash table itself, we try to accommodate the keys and we'll try to see that clashes are reduced. So there are 3 basic techniques in open addressing. One is linear probing. Very simple one. Whenever you find a clash, send that element key to the next vacant consecutive location. Have a look. For example, at this point, yes, this was the place where we got clash, right? So 85, even 85 is going to give you a result as 1, and at 1 it is already filled. So it will go to the next location. Yes, the index value 2 is empty, insert it. Okay, so even 92 will have 1. In the result will be 1, hash function. 1 index value 1 is filled. Go to the next location 2. Even that is filled. Go to the next location. It is placed at index value 3. Okay, it is a simple one, but whenever you try to, placing is okay. When you try to retrieve the data, that becomes a tedious task. So you will be finding a hit, go to the next location. It is simple like linear search. So linear probe will lead to a path to a simple linear search, which raises the complexity. So I'll better go for quadratic probing. In quadratic probing, and here have a look at this function. So the hash of key plus I square mod 7, where 7 will be, n will be generally a prime number. So, and the I value starts from 0, 1, 2 and so on. So, if you find a h of key mod n as a clash, then again calculate 1 square mod 7 mod n. If this is a clash, h of key plus 2 square mod n. So there will be a rare case of getting a collision. Quadratic probing, right? And the third one is a double hashing. That is, if you get a clash with the primary hash function, go to the second function. These are two different functions I'm going to use over here. In quadratic probing with the same hash function, I was changing the variable values, right? But here I'll take two different functions. If with the primary function there is a collision, I'll go to the secondary function. That is the second hash function. So here I have taken key mod n, and the second one is key p minus key mod p, where p is a prime number. Guys, you can have any number of functions. It is not that double hashing means only these two functions you have to take. H1 is the primary and H2 is the secondary. No, not at all. You can take any two functions as the two hash functions which you are going to use, and double hashing is the method you are going to adopt. Okay, so these are the three types of open addressing to overcome collisions when handling hashing. Okay, so then what are the applications of hashing? Best method or best application I can see is digital signatures, then construction of MAX, that is message authentication codes, because we feel that digital signatures must be unique, MAC addresses must be unique, right? So to generate these two, we go for hashing. Error checkings, error handling, we go for hashing. That is basically for authentication. Generally, in case of authenticating things, we look for uniqueness, right? So to attain uniqueness, hashing will be the technique which is used inherently. Right, guys? So with this note, I would like to conclude that we have gone through different types of advanced trees and hashing technique. I hope this lecture was quite simple and understandable. If you want to check on deep into what these techniques are, how the things go on for further examples, do visit our channel of IARE, and you can find loads of content over there. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.